Welcome, Team 1, and Team 1's presentation. Kelly, we're ready. Take us to your team world.
Okay, hi, I hope everyone's doing well. I believe we are the last team to go, so I am sure you're familiar with how to get to teams. If you click on this blue sign over here that says to Team World Transport Area, that will take you to a wall of signs with all of the team worlds listed on it. And then once you're there, if you'll just go ahead and click on Team 1, that will take you to our world. Hello everyone. It looks like everybody got here okay. If anyone finds themselves in a space that appears to be below the building, you can hold shift and press the plus key and that'll bring you into our main space. So it looks like everybody's here, so let's go ahead and get started. My name is Kelly DeReese. I'm this team's college mentor. I'm a second-year student at Ohio State studying materials engineering. I've participated in the OPSPARC program several times, 3 times as a high school participant, and this is now my second year as a mentor. And this team that I've mentored this year has worked really hard to prepare a strong spin-off design, and I know they're very excited to start their presentation. So with that, I'm going to hand it off to Hayes to begin the presentation.
Okay, hello everybody, I'm Hayes, and I'm going to be leading us for the first part of this presentation. We're going to switch off from a couple people. So if you look at my laser pointer, it's over here pointing at the infinity band, and we had to press the first floor button to go to the first part of our world. So once everyone's there, we'll continue. And also, while you're teleporting, if you can see, our world is a giant computer, because that's part of our design, which you guys will be able to see a little bit later. So is everybody here? Or everyone's still in? Okay. So this first slide's Nick, and we'll let Nick talk about himself. So off to him.
Hi everybody, I'm Nick Perlacki, and I'm a sophomore at Baylor School here in Chattanooga, Tennessee. And after school, I mix sound at the theater here at Baylor. I currently work in the theater. We're working on a production of The Addams Family. I'm, again, mixing sound for that. And when I go to college, I hope to study to become a radio frequency electrical engineer, work with RF devices in the medical fields, meteorological fields, and space research. And in order to prepare for that, I currently have my general class amateur radio license with the call sign KM4YHI. And so far I've talked to people in the United States, Canada, Germany, Venezuela, Brazil, the Caribbean, and South.
Okay, so if everybody sees my cursor, we got to go to the next bio teleport, which will take us to our next bio. So that everybody is here, we can continue. Looks like just about. Okay. Oh, you guys have to move down so you can see everything. Eric just told me that. But so I'm Hayes, as you can see, and I'm also a sophomore at Baylor School. After school, I do the STEAM program, which is where we've been doing our OPSPARC project, and I did fencing for the first semester. One of my main interests is playing the guitar, and I've been playing for around 6 years. As you can see, I have 3 guitars in the picture. I have a fourth one. It's just not in the picture. It's kind of broken, not very good looking. And hopefully in college, I want to be an engineer. However, I'm not fully decided yet. So to our next bio, we again walk through this blue teleport, and then I'll hand it off to the next person there.
Alright, so my name is Atherton Mook. I'm the twin brother of Hayes. I'm a sophomore at Baylor School, and I'm a runner. Like I said before, I love running. My race of choice would be the mile, and my current record for that was 5:02 when I made it, but I've gotten it down to 4:53. And I play my share of video games. I like computer programming, like most of the other people on this team. And this year I've taken Computer Science 1 and 2. I'm also in Chinese 400, and we'll take AP Chinese next year. And my friends and I own our own company. And like I said, I have the twin brother Hayes.
Okay. Yes, like you guys said, I've known Atherton for 16 years, longest on the team. And with that being said, again through the portal to get to our last presenter for their bio.
Hello, I am Eric Fong, the last Pascal programmer. I am a sophomore at Baylor, like everyone else, and I've been enrolled in the fencing program for 2 years and the choral program for 5. My favorite subjects here are math and science, and here is, I have been the Chattanooga Boys Choir for 7 years, and I'm the oldest choir there, Cantabile Choir. I'm a bass too. And in the future, I plan on majoring in something like computational science or applied mathematics. And I also have an interest in the developing field of quantum computing. If you go to the portal here, it will go over to the next set of slides.
Okay, so these are our contribution slides. So shows what each person did on our project. And with that said, I'll give it off to Atherton so we can say his first.
So mainly what I did was kind of the graphics of the whole project. So I designed the layout of the Glogster. I helped with the text, like what actually went into it. I did both of the 3D models of the JWST and the fiber optic. And I made our team logo, fiber rocked it. And I also sketched out our ideas that you'll see later on brainstorming.
Yeah, so I'm next. I was one of the researchers for the Glogster. I helped Eric with that. And I was also one of the main builders of this nice looking computer world we did here. I also posted all the photos, or most of them, all of our slides to our presentation in this world. And I came up with some of our ideas for solving the GC problem.
If you go to the next slide, you'll see I contributed some of the teleporters for our active worlds. I helped Hayes do some of the research for our Glogster. I put up some of the citations in the world, and I also organized this whole floor layout and such you see throughout our presentation. Off to Nick.
That's Nick. I helped design the 3D model of the microshutter array, and I edited the blog and helped do research for it. I also helped construct some of the buildings in the world, and I actually came up with the idea at the beginning.
Okay, so if everyone wants to follow me and click the infinity band over here, it'll take us to our next floor, and we will have Atherton presenting that part.
Alright, so once y'all get up here, I'll show you where we start. Yeah. So we start over here, identify the problem. And so our team was faced with the problem of creating spin-off technology from the JWST telescope. And considering the amount of time and effort spent on the JWST, using the new technology developed elsewhere is highly desirable. So the new application, once we figure out what it would be, it'll be improved over time because it'll be reinvested, the business that'll be made. We'll reinvest the profits back into itself. It will have funding from outside sources to make it better. And so the main technologies in the JWST that we had to choose from were the sun shield, the micro shutter array, the folding mechanism, the power mechanism, and the golden reflector. With these technologies, we had to consider the cost of production. Is our product already on the market? So are we making something new? The current status of the current status of the technology we choose to use. So, like, is our product actually better than what is already out there? And then over here, where I'm pointing, we looked at other teams like from previous years and see what technology they chose. And the micro shutter array was very rarely used. And we saw the potential, and that's what we chose to focus in on. And with all the ideas we come up with, we need to consider the profitability, like the more money the better, the ease of creation, so how much new technology needs to be made in order for our product to work, and if it solves the grand challenge problem, which would be like our product solves a big problem, as in like global warming, world hunger, stuff of that nature. And then here is how we scored them on our Excel, or on our decision rubric that we made. For profit margin, if it gets 41 to 50%, it scores a 5, and as you go down, the score decreases. And for percent of components, like how much of it is already made, if already of it's pretty much made, you get a score of 5. And if you have to develop almost all of it, new technology, you get a score of 1. And then for the market share, would be like how much of the market your product would actually take. So if it would, in our case, fiber optics, if it would replace all fiber optics, or if it would only replace a little bit. So if it takes almost all the market, you get a 5. If none, you get a 0. And then grand challenge is how many grand challenge problems you solved, and how well you solved them. The more and the better, you get a score of 5, and the less and worse, you get a score of 1. And so we chose, or out of all the designs, we chose the fiber optic. And you can see the decision rubric back on the other side of the room from the Excel sheet. I'm trying to point to it. And the fiber optics had the score of 15, which is the highest, and the second highest was the ghost hunting equipment using infrared. And all of our ideas are outlined right here on the wall. And the first idea we had was using the infrared camera to hunt ghosts and make a TV show, which really started out as a joke, but we decided to include it in here because we thought it was funny. So some pros of that was hopefully it would make lots of money because it would be a popular TV show. We would become famous and we'd catch ghosts. But really the big con is that it's fake. The show might not take off, and we might not actually be able to catch ghosts, and it's not testable. Our second idea, which is the one we chose, is the fiber optic array. The pro is that it vastly increases the bandwidth and how much data you can transfer in a smaller or the same size. It has a huge market potential because this is better than every other fiber optic out there. But the con is that it's expensive, and we'll have to improve the technology a little bit, as in make the doors open faster and make them last longer. And our second idea is making a solar farm, which is you'd have the reflector from the JWST all point up towards this tower where it would heat up water and it would turn into steam and turn a turbine. So the pro is it's pretty simple. You just all have them pointing up, and it's clean energy, as in no carbon footprint. But the con is, well, it's high maintenance. You have to wash all the reflectors. You have to keep them clean so they reflect a lot. And it takes up, you'll need a big field. It takes up a large area. And it's probably too expensive to have lots of gold reflectors for power. So our next idea is using the infrared camera mounted on a robot for policemen or other law enforcement agencies to see through walls. So the pro is it might save lives, as if the policeman didn't have this, a bad guy, he might catch him by surprise and kill him. And he doesn't actually have to be at the site, so he could be like a mile away controlling the robot. But the con is it would suffer from outside infrared interference, and you cannot see through every wall. Like you couldn't see through a thick concrete wall, for example. And it would be very expensive because you need the whole infrared camera from the James Webb Telescope. And then our last idea isn't a new technology, but it's using the James Webb Telescope to search for life in the like aliens in the outside universe. And the pro is it might find life, and the whole thing is already built, so you don't have to develop anything new. But the con is it would take away time from other uses of the telescope, and it might not actually work. So I'm going to hand it off to Nick Polacki.
All right, everyone, it's Nick. More on the reason we selected this design is it's able to take a lot of information and put it into a smaller area than conventional fiber optic cables. So it acts as a really efficient use of space and materials in order to transmit a lot of data. And it can use mostly all current technologies in order to build the product. But and it's being used in basically the same way as it would be on the James Webb Space Telescope, the micro shutter array, that is, because it doesn't have to be modified in any way, really, because you're just taking the light that would come out of a single LED behind the micro shutter and opening and closing the doors to emulate what LEDs would normally do, turning on and off in a conventional fiber optic system. But you're able to fit many, many more pipes in one area, and you can actually fit 62,000 of them in one spot. Now, a couple of problems with it is you'd have to develop, or you'd have to work 62,000 graphene semiconductors to receive the light. You'd have to work that into a very small area, about the size of a postage stamp, which is quite doable, but maybe a little expensive. And the other problem is we may have to make the micro shutter array a little more efficient and more durable, because when NASA tested 37,500 shutters by opening and closing them about 1 million times, they noticed that 11% of them were stuck closed, and so we would have to make it a little bit more reliable. And also, theoretically, our shutters could reach a very high rate of speed data transfer, but right now they can only reach 30 open and close cycles per second, which could be a little inefficient. But once we improve, or if we were able to improve that speed, we could definitely increase the rate at which data was transferred. So if you want to follow me over to the InfiniBand port on the wall, we'll go upstairs and continue on with the physical design. Okay, since everyone's here, basically, once again, our design would allow for a lot of data to be transmitted through a very small space. Once again, would require some improvements in the microshutter array, just durability and speed of opening and closing cycles per second. But overall, it would work. And in order to transmit the data, we could actually use graphics processors to have to reach the theoretical capable speed of data transfer, because current Ethernet cards could not handle it, but graphics processors could handle the output through some of their pins. The reason we decided on this is, according to IT experts, their number one bottleneck is the rate at which they can transfer data. And since this design allows for a really high transfer rate of data in a really small space, it could really be effective in the market. And hopefully we'll be able to work with current manufacturers to get the fiber optic cables needed. And we really wouldn't have to develop any more new technology in order to get it marketed. We just have to put it all together. And we'd be able to work with large data analytics firms, national labs, data centers, large companies, things of the sort, to get it started and get them buying it and get them testing it. And once we could get it working with the larger guys, we would hopefully be able to market it to the average customer and to the general public to allow our whole infrastructure, our whole internet infrastructure, to be built around this product. And one more thing, if you come down over here where I've got my laser pointing, the theoretical limit to the speed of the device, just taking into account the current limit of single mode fiber optic cables, would be around 310 terabytes per second. Now that's taking the 40 gigabit per second transfer rate that is standard right now and multiplying it by the 62,000 different shutters that are in the array. Now, of course, we would still have to increase the shutter speed, but if we were able to do that, it would work because the required fiber optic strands with the correct diameter already exist. So, once again, we wouldn't have to invent those. And the array size could allow it to be implemented into current computers and servers without heavy modification. For instance, we could put it on a PCI card where current companies could just open up their servers, plug in the new microshutter array, and go ahead with it. And with that, I'll pass it on to Eric.
Okay, hello. We're going to go over here to the JWS model of the JWST. As a brief overview, some of the strengths about the model is it's able to view astronomical phenomena over vast distances with pinpoint accuracy using microshutters and the top-notch sun shield. Of course, it is very expensive, and there are many moving parts which could fail, and humans would be unable to repair them. On the next slide, you'll see it shows the model fiber optics interface. Some of the strengths of our thing is it has high bandwidth, and it technically already has a lot of the parts already exist as a technology, and it would be a very lucrative product to get. Some of its weaknesses is potential durability issues, and the shutter speed might be inadequate. For the marketing, our target market would just be for data centers, and about 8% of the cost is just for networking items. Building a data center can cost up to $535,000, and the data centers really rely on speedy communications to make sure information is transferred efficiently and quickly between machines. Mainframes would also probably use this a lot because they need to route massive amounts of data very quickly to keep networks functional, and customers happy. And just to tell how well this equipment is working for companies, we could just survey how much data centers have spent on networking equipment and whether or not they have just been close to experiencing a bottleneck. Of course, funding this, commercial partnerships would be indispensable to fund this project, because if companies can help make networks faster, then it would be in their favor to fund it. If we go back here, we can see some of the tools we've used for our models. We used Google SketchUp, we used Google SketchUp to, Atherton used Google SketchUp to make the two models you see here, and we also used Glogster to make the beginning poster. I used Accutrans to help import the models and shrink them so they would show up, and we used Google Drive in Google Docs to store our models and presentation materials. To get our photos on World, we used PhotoBucket, and Photoshop was used to create our logo. And although it's not listed on here, we did use Keynote to make our bios and a few other slides around. And our main method of collaboration was by email, although we did set up a Slack, it just was not used. As you can see where I'm pointing now with my laser, here are some of the skills we have learned. One of the important skills that we practiced was teamwork, because we had to organize this whole project together. And another thing we practice is just better time management. I feel that I have had a better sense of time and can get things done more efficiently. This project allowed us to think creatively and design something new, especially because we didn't have to design everything from scratch. And it's helped us to organize ourselves, and in the future make us manage our lives probably a bit better, or whatever other project we have. This project has taught us how to make a good technological presentation format, and along with making a presentation that allows us to interact with the audience. And because of this project, we have like a chance to better understand the design process, because we also have guidance from our instructors. So in the future, we can apply it to other projects independently. The project has given a strong sense of self-reliance, because each of us had to set up due dates for ourselves and design things independently. We had to work independently of each other and combine our work into one presentation in the end. We have also learned about version control and how to manage documenting what we could have done, and this will help us in the future of keeping track and managing things. On the next slide, advice for future OPSPARCians. One piece of advice I would give to future OPSPARC participants would be to set up due dates so things are done at the last minute, and that way you would not procrastinate, because a lot of unexpected things can arise when you're working on this project. I find it integral to have the Active Worlds wiki on hand, especially for making things like the teleports and modifying objects. Figuring out a way to divide up work is also important, so people can actually get work done instead of like going around trying to figure out what they should be doing. And you should also dedicate a good deal of time for putting the models in World, so you can make sure they're not glitchy, and so they can keep their colors and look nice. Setting up a good system of communication is also useful and important, because it allows you to keep track of things easier. And another just helpful tip for efficiency is launching the Active Worlds executable directly, because I found on my laptop it would not keep all my settings, like controls, and then it would take forever to load. I'll now pass this off back to Hayes.
Okay, so you guys want to look over here at my laser pointer? Oh, wrong button. Never mind, it's not working. But oh, there it goes. Okay, so this is the model that Atherton made over here. This is the microstructure one, and because it was so amazing, it doesn't actually load on some computers, or the colors are wrong. But for some computers, you can see us pretty well. Then if we go all the way across the other side of the room, over here where it's pointing now, this is the JWST telescope model Atherton also made. And again, depending on the computer and that, the colors can be different. So finally, one last thing is we'd like to say thank you to all everybody for coming out here and listening to our presentation. Oh, and one last thing is that we're ready for questions, and if everyone wants to look at the laser pointers, we have a end button over here, which takes us back to our world's main room, so we can get questions there.
Thank you, Team 1. Are there questions from NIA?
Yes, this is Eric Axtall from NIA, and my question is, are there any system bottlenecks that you foresee might cause your theoretical data throughput to not be realized?
I got to answer that question. It's Nick. Yes, and that would just be the maximum physical operating speed of the microshutter. Now that's not been tested, so we're not sure, but if it could reach the current standard, or if each shutter could reach the current standard speed of 40 gigabits per second, then we could reach that speed. But as of right now, the open and close speed of the array does not allow that. If it were modified to be more durable and faster, then yes, we could reach that.
Hi, we don't have any other questions here at NIA.
We have a few questions here from Goddard.
My name is Scott Robach. I'm trying to understand exactly what, I apologize, but what the function of the individual shutters is. Are you using them as the actual optical switch in this transmission device?
Yes, each shutter acts like in a normal fiber optic communication system. You have an LED turning on and off in order to send bits of information. But each shutter would act like an LED by opening and closing to allow light from a central light emitting source behind the shutters. And so each shutter is acting somewhat like an LED.
Take the rate for a single shutter, multiply by your 60,000 shutters, that's the total rate for the fiber optic bundle that you have in your design.
I only got a little bit of that. Do you mind getting a little closer to the microphone, please?
Sorry, our microphone unplugged. Are you there?
Yes, I can still hear you, but I'm not sure exactly what you were asking there. I still haven't heard anything from that last question. If you were asking about how I was getting that theoretical limit, it was just multiplying the the current maximum transfer speed of a single mode fiber optic system times the 62,000 shutters. Go ahead. If it's easier for you, you can also just type your question in the chat box if we have any more. Sorry. Yeah, so currently fiber optic communications are limited in more so by space and material size than anything, because here we would be able to fit a whole lot of data in the size of, or we'd be able to fit, like I said, the theoretical limit of 310 terabytes per second of data transfer in the size of what just 5 normal fiber optic cables could fit that are transmitting at 40 gigabits per second. And so it increases, or it improves on that because we've gone from 200 gigabits per second of transfer speed to 310 terabytes theoretically per second of transfer speed. So that's how it would really improve on the current technology.
And to elaborate on that, currently with the fiber optic technology, it can only get so small because of the LED system. Every other part of that fiber optic can be made smaller, but the LEDs are the limiting technology. So with the micro shutter array, that, since it's super small, all the other technology can also be shrunk down to make it smaller. Thank you.
Yeah, thanks so much for coming out and seeing our presentation.
Thank you for coming and seeing our presentation. Thank you.
Thank you very much. It was good to show to you.
Yes, once again, thank you all very much for coming this afternoon. To get back to the main OPSPARC world, over here there's a column that you can walk into to teleport back to the main world whenever you're ready.